Hello, everybody. So, we're going to start the chapter 9. And in the statistic, the chapter 9 talks about distribution of estimates. So, when we are talking about the estimates, we're talking about a statistic. And a statistic just explains and explores the variation. And from the statistic, we can just get the result and infer it to the population level. And it's called the inferential statistic. So concept of variation in a statistic. Up to now, we have built models based on the data to help us understand the data generating process. For example, we have taken a sample of the data, compute the mean of the variable, and use that mean as unbiased estimate of the mean of the population. Previously, we explained to you why the mean is the unbiased estimate of the population, because first it minimizes the error, and the second it just balances out, and it minimizes square deviation, and it minimizes the absolute value of the deviation. So we know these models are wrong. We know this because there is variation left over from the model, variation that we cannot explain. We have squeeze the error variation down as far as we can, and we have a good sense of how much error variation there is. We can measure it we can use the sum of a square, assess variance, sum of a square divided by the average, so sum of a square average of the sum of a square, or a standard deviation, and get the sense of how much error there is around the model. But these estimates are also affected by another kind of the variation. We call them the sampling variation. Remember that when we start to say, for example, we have the data is equal to model plus the error, and we represent the error can be explained and unexplained. When it's unexplained, so we have the two kind of the error that is happening. We have the real variability, which is from the sampling error from the system itself, and we have the sampling variability or induced variability, which is due to the sampling, right? So how much error there is, and we said what tool we can use. But these estimates are also affected by other kind of variation. We call the sampling variation. We make the best estimate of the population parameter we could base on our sample of data. But if just by random sampling we had ended up with a different sample, our estimate of the mean would be different. Variation in individual score around a mean is something we can see by making a histogram of our data. There was a question that asked why we have to make the histogram. So if you make a histogram earlier, you can see the variation that exists in your data, right? So, but variation in an estimate from a sample to sample is something that we generally can't see it at all, primarily because we only have one sample and we know that there is a sampling variation, but it's not easy to gauge how much sampling variation there may be. Take, for example, the variation in time length in our sample of the 157 students. Our empty model is indicated by the blue vertical line. The mean is 60.1 millimeter. We know this is the best estimate we can make of the mean of the population, but we can clearly see how imperfect it is, right? So, but what about the error in the estimate of the mean itself? We only can see one mean in this histogram, yet we know that this is just one of many possible means we could have found if we had taken different samples. This is what we want to find out in this chapter, not just how far off the mean is as a model of our particular sample, but how far off the mean is as an estimate of the population mean. In this chapter, we will introduce the concept of sampling distribution, not the sample distribution, but sampling distribution, which is distribution of an estimates across many possible samples. We will start by exploring the problem of the sampling variation in estimate. We then introduce the sampling distribution as a solution. So we say we have a sampling variation, but what do we do? So our solution might be just using the sampling distribution as a solution, show you how to make one, and finally how to use one to ascertain the accuracy of a statistical model. Exploring the variation in an estimate. To explore the concept of variation in estimates, let's go back to an example we explored in chapter 3, the throwing of the die. We start there because we know that DGP, and because we know what it is, we can investigate the variation across the samples using simulation technique. We know and we confirmed earlier that in the long run of a population of the die rolls has a uniform distribution. If we roll a die one time, we don't know if it will come out 1, 2, 3, 4, 5, or 6 even. But if we throw a die 10,000 times or threw 10,000 dice all at the same time, we should end up with a uniform distribution. Note that we just picked the 10,000 as a really big number, but it could have been any big number. So using the resample function, we simulate this one. So if you use the resample, you simulate the 10,000 die roll. So if for us, if I want to just make the sample, uniform sample of the 10,000 die roll, and it would take a long time for doing that, because the 10,000 just rolling a die, it's a long time for just getting over with this, and takes them many times. But if you just do the resample in the R, it should be in a few seconds. So we have the giant sample. So we have a giant sample that goes to resample. Then we plotted this distribution in the histogram below. So you can see that distribution is almost perfectly is uniform, as we would expect. But it's not perfect. There is some tiny variation across the 6 possible outcomes. We will learn in chapter 3 though that if we take a smaller sample of the die roll, let's say 24, we get a lot more variation among the sample. So if we get this small sample size, we get more variation. And perhaps most important, none of them look so much like a population. Here's a code we use to randomly generate a sample of N24 die rolls. So we have the sample that we can do the resample of the 1 and 6, and we have a 24 die roll. Each time we run this function, we got a different looking distribution. Here are a few examples of 24 die rolls. So we put them in density plot, and so we could appreciate how much different we see over all these shapes. Let's talk about from sample to estimate. Up to this point, we have discussed sampling variation in a qualitative way. We can see that the samples are different, and also none of them look very much like what we know about the population looks like. But now we want to go further. Imagine that we didn't know DGP of this distribution, and we were analyzing one sample in order to find out. We know a lot more about how to do this than we did in chapter 3. Use the data camp we know to generate the sample of the N24 die rolls and save it as a sample 1. We added additional code to print out the 24 numbers that result and then calculate the mean of 24 numbers. So if we calculate the mean of 24 numbers, we end up with a 1 number, which is 3.875. Our sample of N24 had a mean of 3.875. If this were our only sample, we would use the 3.875 as our best estimate of the population mean. But because we know what the DGP looks like, we can know in this case what the mean of the population should be. How can we figure out what the expected population mean should be? How I can just figure out what's the expected population mean? So we can just simulate a very large sample of the die roll to calculate the mean. The mean is the average of these equally likely outcomes. And why the mean is a 3? Because it's a half of the 6 is not correct. Is not correct. If you roll a die 6 times and get a different number each time, the mean should be 3.5, the average between 1 to 6, not the 3. And the mean also can be varied by the times that you roll the die. Every time that you roll a die, you might get the different answers. Let's calculate the expected mean in 2 ways. First, let's simulate 10,000 die rolls like we did above, and then calculate their mean. Modify the code in the DataCamp window to do this. And when we simulate just the 10,000 giant samples, we get 3.4895. It's very close to 3.5. Another way to get the expected mean is just to calculate the mean of each of the equally likely outcome of the die roll. Now you get exactly 3.5, which is what the population mean should be. It's the exact middle number of the 1 to 6, and if each is equally likely 3.5 would have to be the mean. But then let's remember our small sample, the mean was 3.875 because we know the true population mean is 3.5. It's easy in this case to quantify how different our sample is from the true mean of the population. The difference is 3.875 or 3.5 or even 0.375. If we simulate another sample of 24 die rolls, do you think the mean would be off by the same amount? No, it is not, because there is no way to tell. So you say someone says, no, it will be closer to the population, but there is no way to tell. Try the simulation below and say what you find. So every time you would get a different number. So actually there is not any way to say it. But we know in this case that the mean of the population is 3.5, but if we were trying to estimate the mean based on our samples, we would have a problem. The two random samples of the N24 we have generated so far produce two different estimates of the population mean. And let's look at the few more samples, but let's not bother saving in the result of each die roll in each sample. Instead, let's just simulate a random sample of 24 die rolls and calculate the mean all in one line of the R code. Try running the code to see what the mean is for a third random sample of 24 die rolls. So far we have generated a diverse group of the sample means and no two are alike. Examine the three sample means we have generated so far. Given that the true population is that, what do you think is the highest sample mean that you would get? How likely is that you would generate the sample mean of the 6? It's very unlikely, but it is possible that you just draw a die and every time you get the 6, but still it's possible. So it's not there is not a possibility in the statistic. The good thing about the statistic is that everything is possible. We are moving to the next section, which is a 9.2 sampling distribution, a way to see variation in an estimate. So now we tell you we are seeing that much variability, but what's the solution to come with that variability in estimate? Even though we normally would only have one sample and one estimate of the population mean, we hope to have conveyed by now that this single estimate is itself generated from a distribution of the possible estimate that could have been calculated based on the different random samples. Based on just the 3 estimates we have calculated so far, based on the 3 random samples. And we know that the estimates, they vary. But how much do they vary, and how far off could any single estimate be? To answer this question, we need more than just to estimate. What we need, in fact, is a sample distribution of means. Sticking with our die example, let's generate more means for the sample distribution of the means of the sample of N24. We can use the do function to rapidly generate the random samples and compute their means. This could be generate the data frame with the means from the 3 samples, like N24. So we do 3 times the mean. Okay, so when we do 3, so it means do it 3 times, and we have a mean. And we have a sample which shows the sample distribution of the mean. We say 1 to 6, and we want to do it 24 times. 3 samples of the N24. So the means that we get is close to 3.5, but they're quite varied. So 3.6, 3.12, and 3.7. And modify the code to generate the data frame with the 10 sample mean. 10 sample mean, so we can just do 10 times, do 1,000 times, do a million times. And we still get something that is close to our mean that we got for the first time. So it is helpful to start thinking about the means of the random sample we are generating as a distribution. In fact, it's a sample and distribution of the means. Just like any other distribution, it is useful to visualize the distribution and examine its shape, center, and spread. We can already say, for example, that although some of the 10 sample means we have generated are lower than what we expect, or higher than what we expect, they seem to mostly be clustered around 3.5. Let's take the 10 sample means we just generated and save them in a data frame using the assignment operator. We'll call the new data frame like the bunch of means, add the code to print out the contents of the data frame. And how many variables you see? When we talk about the variables, we talk about the columns, so we only see one. And the variable name is the mean. So note that the do function returns a data frame with the function, in this case mean, as a variable. Now we have everything. So we have a sample distribution. Now we can make a histogram of the 10 sample means at the vertical line where the population mean is. Okay, so it's a lot easier to look at the distribution of the sample means when they are in a histogram than just a list of the means. In fact, while limits ourselves to 10 sample, let's simulate a lot of sample. Let's try 1,000 and examine the resulting distribution, the sample distribution of the 1,000 means. What do you think will be the shape of the distribution of the mean for the 1,000 samples of the 24 dice? So usually it should be normal because we add a lot of sample, so expect to get something that looks very normal. Okay, so roughly normal. Modify the code below to simulate the 1,000 samples, and we should resample times a mean. We have added the code to plot the means on a histogram and chain on a vertical line for the expected mean of the population. The histogram above shows the count on the y-axis. So what is being counted? Is the means of the 1,000 die rolls, or the data frame of the die rolls, or what's count? Means of the 24 die rolls, not the 1,000 die roll, by the mean of the 24 die rolls. That's important to also distinguish. In previous chapter, we have created histogram we were looking at the distribution of individual units like people, fingers, and countries, so they are discrete. But in this is a new kind of the distribution. This histogram shows the distribution of the sample means, each summarizing a single sample of 24 diodes. This kind of distribution, also called the sampling distribution, be careful when you say these words out loud. The word sample sounds a lot like sampling, but it's not the sample distribution, it's the distribution of the samples. Sometimes we also call this distribution of the estimate. In this case, the estimate calculated from each sample, so it's a mean. So if you look at the histogram, the distribution of the sample means, does the shape vary? Does the shape of the distribution look the way you expected? Yes or no? You can say yes because you expected. You can say no because you didn't expect that. And we know and have demonstrated that the DGP of rolling a die will result in a uniform distribution of individual die rolls. Each die should appear on 1/6 of the rolls over time. But when we take the means of many samples of the die rolls, we end up with something that looks a lot like a normal distribution. It is important to note that distribution of an estimate may not have the same shape as the population distribution, and as we also have shown, the distribution of an individual sample need not resemble either the population distribution or the sampling distribution. It's important to keep these three kinds of distribution straight each time with each own meaning and purpose. In the simulated sampling distribution above, what do the 1,000 mean? So it means do the 1,000 times, right? Do the 1,000 times sample of the 24 diodes. Let's do a little bit messy activity. When the data generated process is rolling a die, which shape will each of these distribution have? So population distribution, it might be uniform. Sample distribution, it may be any shape, right? Basically uniform, but it could vary. And sample distribution is basically is a normal. But the population is uniform. The sample distribution is uniform, but of course it could vary because it's a sample. And for the sample distribution, we always get the normal. So data generating process, the population mean is what? Means of the individuals, right? Mean of the individual diode. Sample distribution is the outcome of the individual diode. Sample distribution is the mean of the sample of the diodes. Now there is a good question. Why we need the sampling distribution over top of everything that's messed up? Let's go back to the problem we started with. How far off could an estimate of the population mean be if based on our simple sample of the N24? To answer this question, we need the sample distribution of the means. Take a look at the sample distribution. We just created 1,000 samples of the N24 diodes, and we can see that the center of this distribution appears to be very close to what we know the population mean to be in this case. But we also can see a lot of variation in the sample means around the population mean. Some of the randomly generated sample means, though not many, are as low as 2.5. Others, though, again, not many, are as high as a 4.5. But this means is that if we had only chosen one random sample of N24, there is a chance that our estimate of the mean could have been off by as much as one, either one lower or one higher than the true population mean. But based on the sampling distribution, we construct that we can say that is unlikely that our estimate would be off by more than one. Sample distribution thus provide the context for understanding the meaning of an individual sample estimate. Earlier in this course, we made a point that to understand what an individual score means, it helps to know what distribution it came from. In the example of the cargo, we saw that we couldn't really understand what the score of the 20,000 points meant unless we know something about the distribution of the cargo scores. If we know that the mean cargo score is 10,000 and the standard deviation is 2,000, then we can see that the score of the 20,000 is very impressive, the 5 standard deviation above the mean. But if we don't know about the distribution of the cargo scores, we are hampered in our efforts to know what the score of the 20,000 means. The same is true of estimates to understand how to interpret and estimate the health. To know something about the distribution it came from, the sampling distribution of the estimate. If we can figure out what the sampling distribution looks like, then we can make some guesses about how wrong our estimate might be or how comfortable we should be in our estimate. One thing that makes sample distribution hard to understand is that they are imaginary, made up. If we are talking about the scores in a video game, we can actually look at the distribution of the scores, but for sample distribution, we are imagining what the distribution would have looked like if we were to do the study many times. This is not easy to understand. Sample distribution gives us a way to quantify the margin of the possible error in our estimate. So far, we have looked at the sample distribution when we already know something about the population. Later, we will show you how to create the sampling distribution when you don't know the true population mean based only on the sample you have. Simulation from a different DGP and learning to say if. In our die rolling simulation, we didn't start with the sampling distribution. We started first by thinking about DGP. Then the population distribution that we found a result from the DGP. After that, we simulated using the sample command the distribution of some individual sample generated by the DGP. And finally, we simulated a sample distribution of the means for samples of the particular size. We have learned through this simulation a lot about rolling die, but more importantly, we learned that each of these distributions can have a very different characteristic from each other. Sample distribution will often look quite different from the population distribution. We could see this clearly in the case of the dice because we know what the population distribution looks like. If we only had one sample and an unknown population distribution, we would need to be cautious in interpreting our sample distribution.